Hello everyone, let's continue with the chapter 3. So this is about the asymptotic notation. We have mentioned this one when we talk about the introduction. Okay, for this one. So for this one is just a new contents which will be used for the complexity analysis. And then we have another one called review of functions and summations. So this one, the reason is that we want to deal with the recurrence relationship. The reason is that when we have algorithm design, usually we involve a loop, correct? Loop, while loop, do while or until, repeat until, anyway, for loop. So recurrence relationship, or we have a recursion call, correct? It's been like a recursion call. So for those things, for all of these things, we may involve a recurrence relationship. Means like Tn equal to a function of Tn minus 1 or even Tn over 2, like this one, correct? Function. So we only know the relationship between the larger problem and the small problems in terms of time complexity. So, but we don't have a final solution for the t. So what is the result? So we need to solve this. This is the recurrence relationship. And the recurrence relationship usually involves summations and some special functions. So for these things, we want to cover them because they are needed. They are needed in the complexity analysis. So you can go to the appendix A of the book. Okay. So if you go to the book, and then appendix, and then summations, and also, okay, I think this one is enough. Summations. So we have different series and so on. So we'll review this one in the slides as well. So if you have time, you can learn by these things first. Okay, so let's go one by one. We first talk about the most important topic for this chapter is the asymptotic notation. So basically, we know we have that 5 notations, and then we already got an initial idea, but we don't have the detailed definition for each of them. So we want to know what's the definition, and also another important thing is that proof. So first one is definition, correct? So in fact, our proof is also based on definition. That means, for example, how we define the big omega or theta or big O, small omega. So that means for these things, we may have a thing. For example, we said maybe fn equal to 3n squared plus log n. We said this is theta of n squared. Correct? You need to prove it. How to prove? In fact, we need to use the definition to prove. So we need to know what is the definition, how to define these 5 asymptotic notations. And after that, we have some examples. We may have some. We may also share you some proof for those examples. But you also have exercise questions to examine your ability to do these things by yourself. Okay, let's do the first one. Asymptotic complexity. So we said that this is to measure the performance for large n. That means we want to know the scalability of algorithm to see whether it is efficient or not when we deal with a large scale problem. Because for small problem, the difference is minor. It's very small. So only we can see the difference when we process large amount of data. So this is that's why we call it asymptotic. Usually we only concern is when the n is big, not consider the smaller n. Okay, so that's quite asymptotic. Whether it's close to some trend or it is bounded by someone. So this is the reason, the asymptotic complexity. And also we only have a concern on the highest order term in the complexity function. So complex function, like my previous example, this one you have n to the power 2 and then log n. In fact, this log n is less than n, correct, in terms of complexity, and then n is less than n squared in terms of complexity. So this is the highest order. So that means we only concern is the highest order, because the lowest order, the low order terms will not have decisive. That means decisive impact on the complexity, on the trend. Only the highest order will decide. Okay. We also don't have interest in the exact running time, because we want to group them into categories. So whether you have n or n plus 2 or n plus log n or 2n plus 1, so it doesn't matter, because all of this one is theta of n, right? Or big O of n and small of n. So that means we said they are equal to each other. If you have an algorithm, you define algorithm like this way, we said they are the same in terms of complexity. And we define the large n. That means we want to find the limit. That means when the size scalability, when the size of input is very large, what will be the performance? So we look at this part, not compare the performance when dealing with small problems, small scale problems. And we use this mathematic notation to handle these things. Okay, large n, highest order, and grouping, and limit performance using asymptotic notation. We have 5 asymptotic notations which are theta. So lower bound, so we call it tight bound, okay? Both lower bound and upper bound. So it's tight. And big O is upper bound, tight or not tight. So this one comparable or non-equal to equal. This one is less or equal to. This one is larger or equal to. This is less, this is larger. Okay, so upper bound, tight or not tight, and the lower bound, tight or not tight, and the upper bound is tight, and this one is this is the upper bound, this is lower bound. Okay, we explain this one by one. So for example, for this one, we define the functions over the natural number n. Why we use n? Just because we use n to decide the size of the problem. Okay, and then we want to know how fn will grow with the increasing of the n. Right? So rather than use just the original n square, we use the f of n belongs to which group. Okay, which group? So that's the trend. We want to know the trend rather than the exact complexity. Okay, so if n squared or 2n squared, they're the same. The trend is the same. So how it will grow? That means the rate of growth. Whether it's n squared or 2n squared, will only decided by the n, the power. Okay, we have main concern is about the power. What is n to the power of 2 or n to the power of 1 or 1.5? And then for this reason, we want to use a set of functions. Okay, set of functions. So in fact, what is the set of function? In fact, just the asymptotic notation. Because after this thing, we have just like you can think about it is a example, okay, example or the representative function inside. So this one, theta of n or n squared, like this one, they are a set because all of these things belong to n square or 2n square or n square plus log n or n square plus 2n plus 3. All of them belong to theta of n square. Okay. So that means that this defines a group. This is a set instead of one function. Okay, we have this complexity function, and this is a asymptotic notation. We define a set of functions. All of this complexity, exact complexity function belongs to this set. Okay, belong to this set. And the notations will describe the rate of growth relationship between the defining function and the defined set of function. So defining function is the one which one will be defined just like this one. Okay, and the defined set of function. Okay, this one maybe you can consider this is this one. Okay, so that means we defined a set. So this is defining, we want to define this one. So just group them into a defined set. Defined set, that means existing there already. So we use this one, defined set. Okay, because you can also have not like this one, theta of n, you can say this one also belongs to big O of n square or big O of n cubic. So because it's tight bound, because theta is tight bound, both upper bound or lower bound. So of course you can use big O. And then if you raise the order, of course, n square is already the upper bound. That means the complexity is less or equal to n square. Of course, if you raise the power to be 3, of course it can become the upper bound. For example, with the trend, this one is lower than this one. Of course, if you raise this power, of course this one can be upper bound. Right? So that means here we use asymptotic notations to represent the defining functions and the defined set functions. Right? This is n square, n cubic, and so on, but with the asymptotic notations. Okay, so we have a defined set unit is 1, n square, and n cubic. This is set of functions, so we can think about it as representative complex functions, and then we can define a set based on this one, theta of 1, theta of n, or big O of 1, big O of n, like this sense. Okay, so that means that anyway you just establish a relationship between one function and one set. This is a representative functions, and then this is a set of functions based on these representative functions. Okay, let's look at the first one, the theta. Theta is seems like the easiest one because it's like equal. Okay? Equal means they have the same complexity, exactly the same, not too big or also not too small. So they are the same. Okay, so we define this one. We give a definition in this rectangle and show the example on the figure on the graph, and then we give the intuitive meaning. Okay, and also give further explanation. So for function gn, that's the example function we said mentioned before, okay, function. And then for the complexity function, for the defining function, we usually use f of n. Okay, so we define theta of g of n is the bigger theta of n. So just saying, right? Just the pronunciation for this one is the big theta of n. And as the set, which is this one, theta of g of n equal to a set. Set function is each one is f of n. F of n meets such condition. What's the condition? we can find 3 positive constants and then make the following holds such that C1, C2 and N0. We can find this three constant, positive constant. N0 is a number. That means we can find a number after n larger than the N0. For any n larger than or equal to N0, we can have just bounded. We can bound it the f of n. We use gf of n to bound this f of n. So f of n belongs to this group, just like I mentioned, n plus log n. All of this one belongs to theta of n. So that means we may not be applicable for all the numbers of n. N just a size of problem. But after some number, we can always find one number. Of course, if you can find one, you can find many. All the things after this N0 will also hold. Will also applicable. So that means we find N0, we can just define the lower and upper bound for the f of n. So f of n is larger or equal to C1 g of n. C1 g of n is also larger or equal to 0. So this one unit the problem, g of n unit with positive, and then C1 is positive because it's time complexity, and also find enough n n0, the larger n0. So that means we can find the lower bound and the upper bound for both bounds defined by one function. If like that, we said this is a tight bound. So that means if you want to prove a function belongs to this one, you have to use the proof by construction. Based on definition, you prove it directly. Test that example meeting this definition. So this intuitively is a set of all functions that have the same rate of growth as g of n. So g of n is a representative complex function, g of n, usually with polynomial. So for this one, you can find the main thing is one is the same. One is the same. The other one is the rate of growth. Rate of growth. This means we are looking at the large f of n, not the small of n. So that means with the size of n increasing, it has the same rate of growth as the representative complex function g of n. So that's the meaning. And g of n would give the name to it. It's called a asymptotically tight bound for f of n. Asymptotically. Asymptotic means large of n. Is a limit concept. And limit. We mentioned it before. F of n, g of n, and n if this one equal to c. Equal to c. That one will be the tight bound. So that means they have the same, c is larger than 0, the same rate of growth. So we said g of n is a asymptotic tight bound. It's asymptotically tight bound. The larger of n tight bound means the same rate of growth. So that means you don't need to keep the previous original exact time f of n. You can just use the g of n to represent the complexity of this algorithm. So this is the reason we want to use it this way. And then another one also can be grouped into this one. Then we say they have the same rate of growth. So we don't see any significant difference in their complexity. We said they are equal. They have the same. They are grouped together. And then you can find even more efficient. Then you can use another g of n. This one is belongs to O(n) square, and then you can find O(n) log n. Then of course we said this is quicker. So this is the merge sort, quick sort, and the heap sort, like those things. And n square, in fact, later we talk about insertion sort. In fact, is n square. It is slower. It's more complicated. Right? Okay, this is the theta notations definition, and then we have examples after, and then we first give more explanations. For the definition for this one, so when the asymptotic complexity of algorithm exactly matches the theoretically proved asymptotic complexity of the corresponding problem, informally when algorithm solves a problem at the theoretical minimum. So this one is given, the definition given by the LIST, National Institute of Standards and Technology, for this agency, government agency in the Gettysburg of Maryland. I've worked here for 1 year as a guest researcher. Okay, so basically this agency is focused on the standards and the test case and so on. I think this department, this agency, has several Nobel Prize winners as well. Okay, they are strong in the basic science like physics, math, and so on, and also in IT and many other things. Okay, is under the Department of Commerce. Okay, so when the symbiotic complexity, this one maybe still is easy for you to understand. Symbiotic complexity, that means we look at a large n. Okay, large n of algorithm exactly matches. So that means when we talk about large n, they have the same. Exact match means they are the same. Matches the theoretically proved asymptotic complexity of the corresponding problem. So this is theoretically proved, means just like the corresponding problem. Sometimes that means we can utilize this asymptotic complexity to represent the theoretically proved. Means it's not practical performance, it's the theoretical performance, because we didn't implement it using any program language, based on any hardware, any platform. So this means we can utilize this to represent its theoretical performance. Use a tight bound asymptotic complexity. Informally, when algorithm solves the problem at the theoretical minimum. Okay. So this means informally when algorithm solves a problem at the theoretical minimum, we can think about this just like we can say theoretical minimum. That means we can use this. You can use this one because it's tight bound, exactly the same. Theoretical minimum, that means you may give different bounds for this complexity when you do theoretical analysis. But this one, in fact, is the lowest bound which you can find to represent the complexity of the algorithm. So theoretical minimum, you may have multiple candidate tight bound, but in fact some are not really tight bound. This one, smallest one, minimum one, that one in fact is the same, is the cut, is the one we should assign to this algorithm. Okay, so for here these are the same. We have some further explanation. Technically, f of n belongs to theta of g of n. So that means any element belongs to this set, of course, will be a member of this set. So f of n belongs to theta of g of n. So we we need to technically write like this way, use the belongs to, because this is a function, is one element. This is a set, okay? Is a set. This is a member, is one element, okay? One element. So, but for this one, we can just simplify the notations from the belongs to be equal, right? Equal means in terms of complexity, asymptotic complexity, they have the same value. They have the same asymptotic complexity. Does not mean they are equal to each other, because this is one element, this is a set. Of course, they cannot be equal. But just for simplicity, we can write like this way. So both are correct. Okay, if you prefer this one, you can write like this one. There's no issue. And also f of n, g of n, each one is non-negative. They can be zero. They can be, because it depends on the n, correct? But non-negative, at least is larger than 0, larger or equal to 0. You can compare with 0, correct? But that means n equal to something, equal to 0. But the unit is positive, in fact, okay? Okay, let's look at the examples. We said if we want to prove one example belongs to this set, one example function, one exact complexity function belongs to this set, we need to use the definition. That's why we write the definition here. For example, we want to prove this one, 10n squared minus 3n equal to theta of n squared. So how to prove this one? Okay. The left side is a function. The right side is a set. We want to prove this one equal. In fact, it's the same as this is belongs to. Right? That means this one can be replaced. Right? F of n can be replaced by this one, and gn will be replaced by n squared. So you need to prove based on this order. Right? Okay. So that means we can say if we want to prove this one, so by definition, you can say, by definition, of course, it's the theta definition. We need to prove exist C1 larger than 0, C2 larger than 0, and N0 larger than 0, correct? Not only larger than 0, correct? Nz belongs to n, correct? Is natural number. N0 is natural number, correct? Okay. We need to prove this one, such that. So the logic is that based on definition, prove by definition, then we just go through the definition, and then we find the C1, C2, correct? We solve the C1, C2. If we can solve the C1, C2, means we can find the C1, C2, and also solve N0. If we can find those, because as long as you can find that this one exists, then done, correct? That means they meet the definition, of course, that they will belong to this set. Okay. Such that for any n larger than n0, we can have two inequality equations, correct? We write it out as 2 because we need to solve C1, C2. The first one is f of n. We know f of n. Okay, we maybe before this one is better we write it out, so make it easy. F of n is 10n squared minus 3n, and g of n is n squared. Okay, so f of n is 10n squared minus 3n larger than c1 g of n. We need to solve c1, correct? C1, C2, and n0 are unknown. All of other things, f of n, g of n, are known. Okay, larger than larger than C1 G of n square. So this is one function. So of course this one will larger equal to 0. There's no problem, right? And then next one is this one. Okay, the second inequality equation. So C2 G of n square larger than f of n. Just replace, okay, substitution. Okay, so next one will be just solve C1, C2, and n0. So let's continue. So this one is holding, there's no need to check because n is a natural number. And this one is 10 minus C1 n square larger than 3n. You can further factor out 1n cat. So you have 10 minus C1 n larger than 0. The second one is C2 minus 10 n square larger than minus n. Cat. And then you factor out 1n. So you have C2 minus 10 n larger than minus 3. Okay. So next one you need to solve C1, C2. Okay, C1, C2 and n. So make this one positive for any n larger than n0. Of course you need to choose n0. So make this one larger than, if this one is positive, this one must be positive. So that means we can get what? So 10 larger than 0, right? Larger than 0, larger equal to 0. And the next one is C2. This one larger than minus 3. Make it safer, right? Minus 3 is larger than 0. If we can larger than 0, of course 0 will be larger than minus 3. So you can make this C2 minus 10 larger than 10 and larger than 0. So this one will solve. This is exactly larger, right? So it's C1 less than 10 and the C2 is larger than 10. So now you can choose, okay? You can choose. So you can choose C1 as long as it's less than 10, then it's okay. So choose the C1 equal to, maybe we can choose 4. Anyway, and the C2 is larger than 10, then you can choose 12. Right? So that means it will make the above, make this star work. Right? And then n, because this one we don't have any special requirement for n, as long as n is larger, is a natural number. So that means we can choose n0 equal to 1. Okay, choose this one. So that means if we choose this one, star will hold. And then you can say by definition we prove. Okay, we prove. So this is the basic idea. That means we prove by definition. The basic idea is prove by definition. We based on definition, we want to get the solutions for C1, C2, and N0, and then we get one by one. Just based on this one, write it out. Okay, follow definition, write it out, and then you solve the C1, C2. Solve C1, C2 because it exists. You don't need to choose a lot. You just only find one to meet. Let it meet. Of course, you need to consider all the C1, C2, and N0 together. So for here, in fact, we factor out n here. When we talk about this one is coming from this one, we got this one. Just because we don't consider n, as long as the n is larger than 1, this one will always can be reduced to this one. This is positive. So that means there's no requirement for n. But for some other cases, some problem, they may have a special requirement for n. Then you need to consider. Similar for this one, n there's no requirement. As long as C2 is larger than 10, this one is always positive. Of course, will be larger or equal to minus 3. So that's why how we solve this one. As long as you can find a number which is less than 10 for C1 and not a number larger than 10 for C2, and the n0 is n0, as long as the n is a natural number, so you can choose a bound which is just 1, correct? Just choose 1. Maybe some cases you need to choose a number which the n is larger than 120. So that's because you have that requirement. For example, this is not n, is n minus 20, correct? So of course you make this one to be larger. You need to choose a bigger value. Okay, with 20, I think you choose maybe 21. Make this one at least is larger than 1. Okay, this is the proof. Of course, this is a little bit messy, so that's why I have prepared next notes. I will release the next notes. Okay, release and then after the maybe the duplicate of page 1, so you can ignore the second page. So this is in fact is even easier. Okay, even easier. So we have a easier one. For example, like the previous one, we have a trick. Okay, we have a trick. For example, this is 10n squared minus 3n, and you have 10 and 3. Correct? 10 and 3. So this is 2. So in fact, we can always choose C1 a little bit smaller, and C2 is a little bit bigger. Why? Based on definition, correct? C1, C2. C1 is the lower bound, C2 is the upper bound. So we said that the complexity is dominated by the highest order. Okay, highest order. So if for 10n squared minus 3n, the highest order is 10. So you don't need to care about other things. So you just consider this one. And then lower bound, you need to make it a little bit smaller. Right? C1 is smaller. You first fix C1, and similarly you fix the C2. C2 is the upper bound. That means it's a little bit higher. Of course, they have the same complexity, but I mean the term, right? The term, the parameter for the highest order, the coefficient for the highest order, make this coefficient C2 a little bit higher than the coefficient of f of n for the highest order term. So this is the idea. So let's go back to continue. So you can find a C1, make it this one will help us because you already fixed the C1 and the C2, make it easier for you to prove. Because you have chosen C1, C2, next one is just only decided n0, right? So we choose the C1 to be 9.9 and the C2 to be 10.1. Lower bound a little bit less, upper bound a little bit more. So 10, you can, of course, you can use 11 and 8, doesn't matter, right? But this one just make it a little bit smaller. The reason this one will make it bigger, smaller, and bigger is just to easily find the n0, not to be very big. If you choose 8 and 11, or even smaller for C1, even bigger for C2, so the n0 maybe will be larger, because we can find that this is the relationship. Okay, this is the 10n squared. This is the 10n squared. Red one is 10 squared minus 3n. So if you choose a larger bound, the 8n, correct? 8n squared. So maybe you need to look beyond for the other value, so larger n0. But it doesn't matter. It depends on your preference. Okay, and then based on definition, we need to have this exist n0. If n larger than n0, we have, so you can find it, we just directly write out the definition, correct? So we know that f of n is this one, g of n is this one, and then based on definition we have this one. We chose this one first, and then by definition we can write exist n0 if n larger or equal to n0, we can have this one hold. So the 10n squared minus 3n is the f of n larger or equal to the c1 g of n, okay? c1 g of n, and less or equal to c2 g of n. So lower bound, upper bound. So that's why if we can use the same gn, then that is the tight bound. And then you solve for each of these two. Because this one is always less than 0, there's no need to prove that part. You just prove this, solve this one in equality, the other in equality. So this one is 0.1 n squared larger than 3n. This one, move this one to here, move this one to the left. This one is move this one to the right, so it's 0.1 n squared. And this one keep it in the other side. Solve this one. So cancel out 1n and then multiply by 10 on the left and right together. You get n larger than 20. And for this one, factor out n. As long as the n is positive, larger than 0, then it hold if equal to 0. But because we are looking at a natural number, there's no need to consider 0 or negative. The size of the input, there's no 0 input, so we have size input which is larger than 0. For example, you sort 1 number, sort 10 number, sort 1000 number, that will be the size of one. So you need to have these two in quantitative conditions hold for both of them, So you need to hold for this one and hold this one. You do the intersection for both, So like this, one is larger than 30, the other one is larger than 1. Okay, so the common sense is this one, Okay, so finally we find n0 is larger than n0 is equal to, we choose n0 to be 30. So we can write it out again. For any n larger than n0 equal to 30, we can have this 0 less than c1 g of n, less than f of n, less than the less or equal to c2 g of n. So by definition we proved, We also showed their relationship. What's the relationship between 10n squared and minus 3n, the f of n, and the 10n squared? Because this is the dominating part,